Hi, welcome to another session of Circuits and Networks. In today's class 8 under two-port networks, we'll see problems and solutions involved with a pi network as well as T network. Here you can see I have taken two examples and we need to find out one parameter. So I'm finding out here Z parameter or ABCD parameter or Y parameter, and let me convert the one parameter into another parameter that we have seen in class 7 also. I'm sorry I have taken long gap to again come with the new video. There was some constraints that I was unable to make some videos. So anyhow, I'll continue from this class session onwards. So there will be no gap in the future classes. Okay. So let us begin with the first problem. Find y parameters, ABCD parameters, and H parameters from Z parameters for the network shown in figure 1. So here you can see we have a T network supported by input voltage, input current, and output voltage, output current. So for this, we need to find out the different parameters, that is admittance parameters, transmission line parameters, hybrid parameters, and that we need to obtain from Z parameters. So here I am going to teach you the exact solution as well as the conversion technique. Okay. So what we know from the basics of Z parameters, the Z parameters are given by equation 1 and 2. This is familiar. We have seen this equation in our previous two-port network classes. So you can easily derive these values of equation 1 and 2. From this, we need to find out Z parameters. So how do we do that? For that, first we have to open circuit the second port, that is this output port. When the output port is open circuited, this 2 becomes dummy because when output is open circuited, I2 current is 0. When I2 current is 0, so no current is flowing in 2 ohms, and hence we are left over with this figure 1a, which is derived from figure 1. So here you can see 2 ohms, it is treated as dummy. So hence we are left over with this particular reduced network. From this we can easily obtain V1 in terms of I1 and V2 also in terms of I1. How? With the help of Ohm's law. So we know that V1 is equal to, this is 1 plus 3, 4I1. Hence we get the value of Z11, which is equal to 4 ohms. Now V2 is equal to 3I1. It's a simple Ohm's law applied across 3 ohms. So V2 is equal to 3I1. And what we have obtained? We have obtained Z21, whose value is 3 ohms. Let me treat these two equations as 3 and 4. Now what I'm going to do, I'm going to take this input port and I'm going to open circuit it. So when the input port is open circuited, 1 ohm, which is in series with this I1, this I1 is open circuited and its value is 0. So hence figure 1 changes to figure 1b, and this is a simple loop circuit. So you are going to get the value of V2 in terms of I2, and also I'm going to get V1, which is the measurement across 3 ohms, and according to Ohm's law that is equal to 3I2. So what I'm going to get, V2 is equal to 5I2. Why 5I2? This is 2 in series with 3. So V2 is equal to 5I2. And as I told you, V1 is a measurement of voltage across 3 ohms. So V1 is equal to 3I2. With this two parameters, I can easily obtain the output impedance as 5 ohms, which is treated as equation 5, and transfer impedance, which is equal to Z12, which is 3 ohms. So with equations 3, 4, 5, 6, let me frame the Z parameters. So Z parameters are obtained as 4, 3, 3 and 5. Now in order to obtain the other parameters like admittance parameters, transmission line parameters and hybrid parameters, we have seen the technique to convert Z parameters in terms of other parameters. So that conversion we can witness in our class 7. So already we have derived all these things. You please check into the class 7 for the conversion. I am directly applying the formula in order to obtain admittance parameters from impedance parameters. For that, I have to calculate the modulus of impedance parameter, that is delta z, which is equal to z11 multiplied with z22 minus z12 z22. So here I am going to get the value as 4 into 5 minus 3 square, that is 9. So 20 minus 9, which gives the value as 11. So this is the 11 ohms value of the delta z, and I know that admittance parameters can be obtained from impedance parameter from this standard equation y is equal to 1 by delta z. Just replace the parameters of impedance, that is applying inverse to this matrix. I am going to get 1 by delta z. So z11 replaced by z22, z12 replaced by minus z12, z21 replaced by minus z21, and z22 replaced by the cofactor z11. Now, since I know these values, I am directly applying the values to this formula. So I am going to get 1 by 11, that is delta z. Z22 is 5. Z12 minus time gives the value as minus 3. So as Z21 value, that is minus 3, and Z1 value as 4. So you have seen how easily we have converted the impedance parameters into the admittance parameters with one technique. That is, I am trying to obtain the Z parameters, and after obtaining the Z parameters, I am determining the Y parameters. Similarly, I can obtain ABCD parameters as 1 by Z21 with the matrix Z11, delta Z, 1, Z2. So simply I am applying these values, that is 4, 3, 3, 5, and delta Z values. So I am going to get ABCD parameters in terms of impedance parameters, which is equal to 1 by 3. This Z11 is 4, delta Z is 11, 1 as it is, Z22 as 5. Hence, the transmission line parameters or ABCD parameters are obtained in terms of impedance parameters. Likewise, the hybrid parameters given by H is equal to 1 by Z22, delta Z, Z12, minus Z21, and 1. So I'm going to apply these parameters over here, and I'm going to get the value of H parameters in terms of impedance parameters as 11 by 5, 3 by 5, minus 3 by 5, and 1 by 5. Now, let us check whether the approach we have done, that is this shortcut method, is correct or not. So I'm going to take an example of admittance parameters, and I'm going to apply the original technique of admittance parameters to this figure 1, and I'm going to determine the admittance parameters, and I'm going to cross check my result with this shortcut technique what I have done. So what exactly I got the admittance parameters? I got the admittance parameters which is equal to y11, that is 5 by 11, y12 which is equal to minus 3 by 11, y21 which is equal to minus 3 by 11, and y22 which is equal to 4 by 11. So here Y parameters we obtain in this fashion, and this particular circuit, that is the circuit or the network which is shown in figure 1, is said to be reciprocal in nature because we have y12 is equal to y21. Now this answer we need to cross check with the original solution what we are going to employ in order to determine the y parameters. For that, I am going to take the output port and I am going to short circuit it. So for admittance parameters, we short circuit the output port as well as the input port respectively. So we have standard equations of admittance parameters in terms of I1, I2, that is in terms of voltages V1 and V2. So when output port is shorted, that is voltage is made equivalent to 0, I am going to get I1 and I2 in terms of V1. So when this is shorted, the 2 and 3 they become in parallel. So the parallel combination gives you the value as 2 into 3 divided by 2 plus 3. So 6 by 5. So this reduced network is shown over here. and that is in series with 1. So I'm going to get the input admittance as well as the forward admittance. That is I1 is equal to Y11 V1, I2 is equal to Y21 V1. So I'm taking the R equivalent for this reduced network. So I have V1 is equal to 1 plus 6 by 5, or 1 plus the parallel combination of 3 and 2. So this will give you the value as 11 by 5 ohms. So R equivalent is obtained. Now according to Ohm's law, V1 is equal to R equivalent I1. So I'm going to get V1 is equal to 11 by 5 I1. In fact, I1 is equal to 5 by 11 V1, so that I can obtain the value of Y11, which is nothing but equivalent to I1 by V1 at output port short circuited, that is V2 is equal to 0, whose value is 5 by 11 Siemens. So this is the value of Y11. Let me treat this equation as 7, and from current division rule I am going to obtain I2 in terms of I1, so that I can easily obtain Y21, whose relationship is in between I2 and V1. Already we have I1 in terms of V1. So I2 is equal to, from current division rule, so you can see this current is flowing opposition to I1, that is why minus. The total current is I1. For this branch, that is current which is flowing in 2 ohms, the opposite or parallel parameter is 3 ohms. So total current multiplied with opposite resistance and whole divided by the sum of these two parallel resistors. So minus I1 multiplied with 3 whole divided by 3 plus 2. So now I got I2 in terms of I1. So what is the requirement? I should get I2 in terms of V1. So I'm going to take the help of equation 7, that is I1 is equal to 5 by 11 V1. So I'm going to substitute I1 in terms of V1 over here, so that I'm going to get the value as minus 5 V1 by 11. This term as it is 3 by 5. So here the like terms will goes off, and hence I'm going to get the value of forward transfer admittance denoted by Y21, which is equal to I2 by V1 at V2 equal to 0, whose value is minus 3 by 11 Siemens. So this I'm treating as equation 8. Now let us inspect with port 1. So input port is shorted. So the input port is shorted, implies V1 is equal to 0. Now 1 and 3 are in parallel, and R equivalent will be equivalent to, looking at from the output port side, 1 parallel to 3 is in series combination with 2. So from standard Y parameters, we are going to take V1 equal to 0 in this equation, so that I am going to get I1 in terms of V2 and I2 in terms of V2, so that I can get the value of Y12 and Y22. So R equivalent, as I told you, 1 parallel to 3 is in series with 2, which will give you the value as 3 by 4 plus 2, whose value is 11 by 4 ohms. Hence, V2 is equal to 11 by 4 I2, and hence I2 equal to 4 by 11 V2. So that we can obtain the value of Y22, that is output admittance, at V1 equal to 0 as 4 by 11 Siemens. This I am treating as equation 9. And now from current division rule, let me obtain I1 in terms of I2. So here you can see I2 is opposition to I1. In fact, I1 current is dependent upon I2 current. So I1 is equal to minus, because the opposition, I2. Now for this branch, that is 1 ohm, the opposite resistance is 3. So 3 multiplied with the total current I2 divided by 3 plus 1, that is the sum of these parallel resistors. And now From equation 9, I can get I2 in terms of V2 as 4 by 11 V2. So I'm just substituting the value of I2 over here. So it becomes minus 4 V2 by 11 multiplied by 3 by 4, and cancelling out the like terms, we are left over with y12, which is equivalent to minus 3 by 11 Siemens, and this we are treating as equation 10. So from equation 7, from equation 8, from equation 9 and 10, we are going to obtain the y parameters, which is equal to y by 11 minus 3 by 11 minus 3 by 11 and 4 by 11. Now this output what we got using the admittance parameters is quite similar to the shortcut technique what we employed in order to obtain y parameters from z parameters. So this is how you cross check your result. I hope you understood this approach as well as the previous approach, and you can compare the techniques, and hence you can formulate y parameters in a shortcut way as well as in a natural way. Let us go with another example. Find ABCD parameters from Z parameters for the circuit or for the network shown in figure 2. Circuit is the closed path. Network, you can have an open circuit on either side of the networks. Okay. So ABCD parameters we need to find out. So let us go with the normal approach, that is to find out the ABCD parameters. The standard ABCD parameters are given by equation. V1 is equal to AV2 minus VI2, and I1 is equal to CV2 minus DI2. Now what we need to do? We need to take the output port and we have to open circuit it. When output port is open circuited, this I2 goes to 0, and we are left over with figure 2a from figure 2. Now you can see we can get V1 in terms of I1 as well as V2 in terms of I1, and let us see what we are going to get. The transmission line parameters, that is we are going to get A as well as C. A is equal to V1 by V2, that is the reverse voltage gain, and C is equal to I1 by V2, that is the admittance parameter. Now from looking at input port side at figure 2a, this 1 and 2 are in series and they are in parallel, that is 3 is in parallel with 2 and that combination is in series with 1. Hence R equivalent is equal to 1 plus 3 parallel to 2, which will give you the value as 11 by 5 ohms. So that V1 is equal to 11 by 5 I1. I hope you understood this approach that we are employing since our previous classes in order to determine V1 in terms of I1 by finding out the R equivalent. Now once we got the value of V1 in terms of I1, let us see what we are going to get another value. Since I2 is equivalent to 0, so we cannot take I2 over here, and V2 is the voltage measurement across 2 ohms. So naturally it's a closed circuit, figure 2a. So there should be a current which is flowing in this 2 ohms. So that current I am treating as I1 dash, which is flowing over here. Now we are assuming I1 dash to be flowing according to I1. So I1 dash is equal to the total current, because the flow of the current of I1 dash and I are both are the same. That is why here it is positive sign. So I1, for this 1 in series with 2, the opposite parameter is 2. So 2, it is over here, divided by 3 plus 2. That is the sum of these parallel resistors. So once I am going to get the I1 dash, I can easily obtain the value of V2. So V2 is equal to 2 I1 dash. And I1 dash I am substituting the value as 2 I1 by 5. So 2 I1, this 2 it is as it is, and I1 dash is nothing but I1 multiplied with 2 divided by 5. So 2 by 5. Hence I am going to get V1 by V2. Just take these two equations. V1 I have 11 by 5 I1, and V2 we got the value as 4 I1 by 5. So just take these two ratios and we are going to get the value of A, which is equal to 11 by 4. It's a reverse voltage gain, and voltage gain doesn't have any units. So A is equal to 11 by 4. Now observe this equation. I1 is equal to CV2. So I1 is equal to CV2. With this, we can take this equation, that is V2 is equal to 4 I1 by 5, and we can get the value of C is equal to I1 by V2 at output current is equal to 0, which is nothing but 5 by 4. Let us treat equation 1 and 2 as the values of A and C. So it's a standard approach what we employ in order to determine the ABCD parameters. Now what we have to do? We have to take the output port and we have to short circuit it. So when you're going to short circuit this output port, you have this figure 2. When you're going to short this, that is, this point is going to get shorted. The short wire, it will overcome this 2 ohms, hence 2 ohms becomes dummy, and you are left out with the T network connected with short wire. So this is how the circuit looks like. Now V2 is 0 but not I2. Is this clear? Now from standard ABCD parameters, we have V1 is equal to minus VI2, I1 is equal to minus DI2. So I'm going to take R equivalent looking at the input port side. So I'm going to get R equivalent is equivalent to 5 by 3 ohms, because you have 1 and 2 which are in parallel connected in series with 1. So 2 by 3 plus 1 gives you the value as 5 by 3. So V1 is equal to 5 by 3 I1, and from current division rule I can get the value of I2 in terms of I1 as I2 is equal to minus I1. Why minus? Because of the opposition side we need to find out the current in 1 ohm, opposite is 2. So 2 divided by sum of these parallel resistors, so 1 plus 2, whose value we are going to get as 2I1 by 3. So 2 by 3 I1. I1 just we got the value as 3V1 by 5. So minus as it is. So 3V1 by 5. So remove the like terms and we are going to get the value of I2 in terms of V1 and also V1 in terms of I2. So V is equal to minus V1 by I2 at V2 is equal to 0. Value is 5 by 2 ohms. Just cross check these values and substitute the value. You're going to get B is equal to 5 by 2 ohms and D is equal to reverse current gain, whose value is 3 by 2 ohms. So overall, the transmission line parameters from equation 1, 2, 3, 4, we are going to get as 11 by 4, B value as 5 by 2, C value as 5 by 4, D value as 3 by 2. So this is the exact approach what we employ in order to determine the transmission line parameters. Now let us go with the shortcut method, that is I am going to take the standard figure, I am going to apply impedance parameters, that is V1 I have, V2 I have, and I'm going to take output port and I'm going to open circuit it. When I'm going to open circuit it, this is how the circuit looks like. So figure 2 changes to figure 2a, and these two parameters, you have V1 and you have V2. So we are going to get V1 in terms of Z11, V2 in terms of Z21, and hence V1 will be equivalent to 11 by 5 I1 and V2 is equal to 4 I1 by 5. So that we are going to get this I1 dash is the approach applied according to the technique what we have applied already. So this I1 dash is replaced here as I1 of 2 by 5. So Z11 will be equivalent to 11 by 5 ohms and Z21 is equal to 4 by 5 ohms. Similarly, when input port is open circuited, this one goes off and V1 is shifted towards 2. That is what is done over here. So this is a closed circuit. So figure 2b is obtained from figure 2, and we need to make I1 equivalent to 0 in these two above equations, and we are going to get V2 in terms of I2 as well as V1 in terms of I2. So V2 is equal to 6 by 5 I2. How you got 6 by 2? 6 by 5. You have 1 and 3, 1 and 2, which becomes 3. 3 is in parallel with 2. So 3 into 2 is 6 divided by 5. So that is why we got the value as V2 is equal to 6 by 5 I2. And V1 is nothing but 2 I2 dash. So I2 dash is nothing but I2, the total current, And for this 3 ohms, opposite is 2. So that is why it is 2 divided by sum of these parallel resistors, that is 3 plus 2. And V1 is equal to 2 I2 dash. So replacing I2 dash with 2 I2 by 5. And hence I'm going to get Z22 from this equation as 6 by 5 ohms. Whereas Z12 is equal to 4 by 5 ohms. And hence we obtain Z parameters for the given circuit, which is shown in figure 2. So after obtaining the Z parameters, which is framed in this fashion, I can easily obtain the delta Z value, that is 11 by 5 multiplied with 6 by 5 minus 4 by 5 square, whose value will give you as 66 by 25 minus 16 by 25. That is nothing but 50 by 25, whose value is 2. Now once we obtain the delta Z, I have already shown you the standard equations, what we have already taken as the shortcut method. So ABCD is equal to 1 by Z21, Z12, sorry, Z11, Z22, delta Z and 1. Just replace the values which are given over these Z parameters as well as delta Z. So I'm going to take 1 divided by Z21. Z21 is 4 by 5. So 4 by 5, 1 divided by 4 by 5, open bracket. Z11 is 11 by 5. So 11 by 5 as it is. Delta Z is 2, that is 2 as it is. 1 untouched, it is as it is 1. Z22 is 6 by 5. Just multiply this 1 by 4 by 5 with the interior of this matrix, and we are going to get ABCD parameters as 11 by 4, 5 by 2, 5 by 4 and 3 by 2. Now this is the same answer what we have obtained using standard transmission line parameters. Also, we can obtain H parameters, which is given by 1 by Z22, delta Z, Z12 minus Z21 and 1. And you are going to get the values of H parameters as 5 by 3, 2 by 3, minus 2 by 3 and 5 by 6. Please answer in the chat box whether you have employed the H parameters, the original approach, as well as this shortcut method, and you got the same result or not. So in today's class, we have seen the Z parameters, transmission line parameters, hybrid parameters, and impedance parameters, conversion from one form to another form. I hope you like this video. Please share among your friends, subscribe to my channel, and please press the bell icon for the future notifications.